Morning, everybody. Thank you for coming to the latest iteration of our ICN2 Nano Seminar series. So for those who aren't familiar, there's a two-talk format in the series. So we'll start with a 10-minute talk from a junior researcher, followed by a 45-minute talk, more or less, from our primary speaker. So first up, we have Hugo Gómez, who's from the Thermal Properties of Nanoscale Materials group. He's a PhD student in that group here at ICN2. Hugo, you have 10 minutes, so you can share your screen and the floor is yours. Oh, sorry, one last thing. We'll save questions for both speakers until the end of the seminar. And you can put questions in the chat or in the questions and answers button here in the bottom.
First of all, thanks for the invitation to do this introduction talk in the Nanoseminar. I want to start by talking about a little bit of doing a brief presentation about my research work, which is with title "The Measurement of Heat Capacity in Transition Metal Dichalcogenides by Pulse Heating Technique." I want to start by talking about my collaborators. First of all, my PhD advisors, Javier Rodríguez Viejo and Aitor Lepandia. From the group of thermal properties in nanoscale materials, I want to also highlight my collaborators from ICN2, from the group from ultra-fast dynamics in nanoscale systems that are in charge of doing the transfer of the 2D materials. So to start with this brief overview, I want to say what is the heat capacity for those that doesn't know. Heat capacity is a thermal properties that consists in the amount of energy that is supplied to a material in order to change its temperature. Why is this important and why I'm doing this project is because it has never been measured directly. There are some estimation of what the heat capacities will be in the monolayer by layer structure, for example, but this has never been measured directly, experimentally. So that's why this is so important. How do we measure this property? We do it by calorimetric methods. Calorimetry has been around 300 years, but during the last 30, 40 years, there has been a huge development in this technique. For those that doesn't know what is calorimetry, we can characterize the kinetics and thermodynamical properties of these materials by measuring the heat release or absorbing during isothermal heating cooling process experiments. And yeah, in the heat capacity equation, we can simply take the heat capacity addenda, which is really important in order to know to measure the heat capacity of very small samples, like we are going to measure in these 2D materials. We have here the input power, the thermal length, and also the phase transitions on something that we are not going to take into account here. So this calorimetry started, the calorimeter that we are using started more or less in 1994 with the work of Francis Hellman from the University of California, Berkeley, with this first silicon nitride membrane-based calorimeters. This was also developed by Leslie Allen, the fast scanning thin field calorimetry technique, where we can have very high heating rates and also very high resolutions. And in 1997 in Grenoble, in France, the membrane-based calorimetry in order to be used with the AC calorimetry method. With this technique, we can reach a very high resolution, but the problem is that we cannot access very small or very small areas, which is the one that we have in these 2D materials. So that's why we started to develop in our group. They started to develop a new technique called pulse heating technique back in 10 years ago, but right now we are coming back to it in order to measure our 2D materials. So this is the kind of chips in order to measure the heat capacity that we have. The key point here is that the signal to noise ratio, which is the sensitivity that we are going to have in this technique, is reduced in order that we have a heat capacity of the order of magnitude, at least, of our 2D material. So yeah, the advances in silicon microfabrication and the fact that we can have colorimetric cells with very light dielectric membranes makes the heat capacity of these colorimetric cells even lower. I'm going to present a little bit about the technique that I told you, the pulse heating technique. It was developed in the group back 10 years ago, and right now we are using again in order to measure these materials. We can have very high heating rates, something really important in order to have very high sensitivity. The pulse that we have, so I didn't explain what is the pulse heating technique. In this technique, what we have is a very short pulse in the order of the microsecond scale with a very high current. So by doing this, we can access to the resistance and the temperature of our colorimetric cell, which is the part of the cell that we are heating. And we can extract the resistance and the temperature, and then simply by we can take the heat capacity. So yeah, this the most important thing about this technique is with this a scalable technique. We can have 15 by 15 micron colorimetric cell, and we can access to the whatever material that we are placing in that colorimetric cell. And yeah, and we take a look at the equation of this material. We have here the heat capacity, and then the power that we introduce and the heating that we produce by Joule effect. The heating rate is also really important, and also here we have the power losses that we don't have any power losses, or at least not something that we are going to take into account, because it's of the conduction and the convection of radiation that we are not having in this case. And we did some improvements in this technique in the past year. This was I'm plotting here the resolution of this technique. And before starting with this project, they have a resolution of around 75 picojoule Kelvin. And now with the improvement in this technique and the improvement in the device that we are having, we have 8.8 picojoule Kelvin. This is, of course, taking into account that the spatial resolution of our different chips. So the first thing that we have to do in order to measure the capacity is calibrate the colorimetric cell. How do we do it? Well, we simply start at a lower temperature, taking a range of temperatures that we want, and we start to rise at a control way. We do it at around 50 millikelvin, and then we use pulses of in the range of the microseconds, and then we simply let the colorimetric cell cool down in order to have the reference temperature that we have is the same at every single measurement, and we get this kind of heat capacity of our heat capacity compared with our temperature. Once we have done the calibration of the colorimetric cell, what we have to do is transferring our 2D material, which in our case is molybdenum diselenide, into our colorimetric cell. We do it by mechanical aspiration, and I'm sure that most of you are familiarized with this technique. And we simply exfoliate the materials. We put it in this viscoelastic polymer. We press against our colorimetric cell, and simply by slowly peeling off the flake, it will remain over our colorimetric cell. This is an optical image of our colorimetric cell, and here we can see how the flakes is completely centered around our colorimetric cell. We have colorimetric cells of different sizes. We have 15 by 50 micron and 50 by 50. We will select one another simply by taking into account the size of the flake that we want to study. So once we have to do the transfer, what we have to do is simply measuring again our colorimetric cell, which is the red signal, and the signal that we obtain is the sum of the colorimetric cell plus the molybdenum diselenide flake. We can do this again. We have the 50 by 50 micron. This is the AFM image of our chip, and if we do it in the 15 by 50 micron, we get something really similar. And we have also here the transfer flag and the AFM image, and you can see the signal of this transition method like chalcogenide is a little bit higher, of course. But how reliable are these measurements in order to compare with the real heat capacity, for example? What we have to do, I mean, first of all, something that we can do in this results is do a box averaging. In the box averaging, we can have an improvement in the resolution of the heat capacity by losing resolution in temperature. Here we have a high resolution in temperature, but we don't have so much resolution in the heat capacity. So what we do is doing a box averaging of around 1 Kelvin or around 12 Kelvin, whatever we want, and we get a much cleaner signal. For example, here around 1K, you can see the black line with the colorimetric cell and the red line with the colorimetric cell plus the molybdenum diselenide flake. If we take a 10K box averaging and simply doing the difference between the red line and the black line, we can have here the heat capacity of our flake. If we can also compare this with the calculation of the capacity of bulk molybdenum diselenide. We're using simply this bulk value that we have, that is reported in the literature, and using this heat capacity, the density of the material, we can estimate the heat capacity of a single molar layer by taking into account the lattice parameter of our material. Something that we expect that we haven't done again is to have a softening of the vibrational modes in the monolayer by layer, for example, molybdenum diselenide, because of these kind of materials are not surrounded by the neighbor layers that we have in the book material, for example. So this softening of the vibrational modes, we expect, that we haven't measured yet, to have an increase in the heat capacity in comparison, for example, with the book material. But we have to do more experiments about it. And yeah, the project measurements, we have, for example, this kind of flakes where we have different layers. The main goal is to measure, for example, here we have a single molar layer molybdenum diselenide transfer over this material, and we will simply take the sum of the contribution of each part, and we expect a heat capacity, for example, in this flake of around 15 picojoule Kelvin. And the bulk material heat capacity is reported with this value of heat capacity. So yeah, just to sum up, we have implemented this post-heating technique in mechanical exfoliated flakes. We have done it correctly. We have also done a correct calibration of our empty colorimetric cell, a successful transfer of this flake of our flakes over our chips, and the heat capacity that we are measuring is in accordance with the theoretical value of the molybdenum diselenide bulk. So yeah, to be done in the future, we will transfer and measure thinner flakes in order to reach the molar layer, and we will see what we are expecting about the heat capacity of the softening of the vibrational modes. It's real, and it's something that we can measure experimentally. So yeah, that's it, and thank you very much for your attention.
All right, thank you very much, Hugo. So just a reminder for everybody, if you have questions, we'll save them all for both speakers until the end. So you can post them in the chat or in the questions and answers box here at the bottom. Then we'll do our best to get to everybody. Okay, Hugo, if you can stop sharing so that Professor Duesberg can start sharing and I'll give an intro. So now we have our main speaker, Professor Georg Duesberg from the University of Bundeswehr in Munich. Professor Duesberg studied physical chemistry during his undergraduate at the University of Kassel in Germany, and then was a researcher at the Max Planck Institute for Solid State Research in Stuttgart, as well as Trinity College, Dublin. And he gained his PhD at the University of Tübingen in Germany in 2000. From 2001 to 2005, he worked at Infineon in the corporate research department in Munich, and then 2 years in the thin films department at Qimonda in Dresden. In 2007, he became an associate professor in the School of Chemistry at Trinity College, Dublin. He was a principal investigator in the National Research Institute, CRAN, which is Adaptive Nanostructures and Nanodevices in Ireland. And in 2017, he became the chair of sensor technology at the University of Bundeswehr, Munich. His research focuses on the synthesis, characterization, and devices in low-dimensional structures, and we're looking forward to his very interesting talk today. So Georg, the floor is yours.
Thank you for the introduction, and I'm really sorry that I couldn't make it to Barcelona. It was my intention to come to give this seminar in person and have a look at your beautiful institute with a lot of research on 2D materials. However, this time it wasn't COVID, it was a strike in Munich that prevented me from flying. So I tried to bring across my talk on 2D materials for sensing online. Just one word about the institution where I'm at. I'm at the University of the Bundeswehr in Munich, which is a small university at the south of Munich. So it's not the LMU or the TU. We are located in the south, and we are actually located on a military base, educating German officers. However, as a young university, we are fully accredited. We also can have civil students, and our research and my research is basically based on international students, and I'm participating in all EU projects. And we actually have quite a nice suite of setup at the Institute of Physics for it's a classical semiconductor institute with clean rooms and analytical labs for surface science and electricals, but we have also added quite a few tools to work on 2D material synthesis, characterization, and sensing capabilities. So with this, I would go to the overview. So brief introduction on the applications of 2D materials and electronics and sensing. Then I would like to dedicate it, the first part of my talk, mainly to graphene-based sensors and contaminations on 2D materials and the effects on functionalization. And in the second part of the talk, I would briefly talk about polycrystalline transition metal dichalcogenides, and in particular on some sensors based on platinum diselenide before I conclude. So as you all know, and I know that there's also activity at your institute, there's a lot of perspective for 2D materials and sensing. And so if you look at the sensor market, you can see it's a very rapidly growing market. On the right side, sorry for the German here, it's basically mobile phones and applications for MEMS devices only, where you have talk about pressure sensors, acceleration sensors, and so forth, but also microfluidics and optical MEMS. On the left-hand side, you can see the market for wearable sensors, which is about to really start growing around this time. And of course, here a lot of applications are, again, accelerations and so on, but also a lot of applications in medical, the medical area. And in this area, we have basically also an initiative that you want to, let's say, downscale sensors to make them wearable. The reason is, of course, power consumption and size to make them wear. But of course, you ask the questions, why don't you do research at it and just not buy the Fitbit or the smartwatch? At the end of the day, you need more or want more information. And just to give you an example, I didn't want to expose myself too much, but this is me doing an electrocardiogram a few months ago, and I've been hooked up to spirometry, checking my breath, and then all these electrodes which are attached to my body by suction to do the testing. If you want to do things like this in a medicinal environment, you need more information. That's why it's done like this, because you cannot get the data you need from simple Fitbits. On the other hand, this prevents of moving around outside. And this is exactly the initiative we'll be looking at, all the applications to place various sensors at human beings for long-term studies. And to some extent, 2D materials are sort of deemed to work for these various sensing applications, because you have, besides what you all know, very band gaps and high mobilities, you got in some of those materials a very high stability, yet having flexibility, and you have this very high aspect ratios. It allows you to use this material as sensors, and there are various types of sensors you can use them for, and this is electrochemical sensors or membranes, but I will be talking mainly about chemoresistors or functionalized chemoresistors, which then can act as biosensors, where you simply use absence of bulk to modulate the conductivity through this material. And then we can also have optical sensors slash photodiodes using the transparency of the material and the very band gaps that are available. And at the end of the day, you can also look at MEMS devices, which use the flexibility and the extreme robustness of those materials to be integrated in MEMS devices. So let's have a quick look at graphene and physiological sensors. And what I've been using, and just as a brief introduction, is here monolayer high quality CVD graphene. Even so, I say high quality, it's actually not the highest quality. It was high quality about 10 years ago. But it's, let's say, standard good-ish materials with mobilities around 1,000, which we grow in tube furnaces on copper. And we end up, if you look at the TEM, is nicely crystalline material here. If you use this, you can use this and directly make an electrode for skin in here without any modification. And the integration scheme would be like this. We take the graphene on copper, coated with PMMA, as you do in each wet transfer, as a supporting layer, and then we flip the whole thing around it and put it on tattoo paper with still the PMMA remaining here. And then we can use this tattoo paper basically to attach it directly onto skin. Before that, we have to engineer an electric lead to it, and we use this tegaderm, which is basically medicinal tape, to attach it to skin. But at the end of the day, we have a direct contact of this graphene layer here to the skin electrode. Just as a reminder, the competition is metal-based electrodes, which cause skin irritations, or the suction electrodes, or polymer gel-based electrodes, which tend to dry out over time and cause skin irritations. And the idea is that this very thin monolayer plus polymer layer can really be sort of have conformal or intimate contact to the skin as shown here. And basically we can attach these tattoos directly onto the skin. We did it on the head, but here it's an image on the forearm, and here you see the graphene bits with a bit of tape on top. But at the end of the day, the graphene more or less adheres directly to the skin without any adhesive. And without going into further detail, we started to record first materials. This is a signal for closing a fist. Here, muscle contraction trigger, and this is a signal for waving the hand with the same arm. And you can see they're clearly signals. They are not noise. They can be distinguished, and the people from our medicinal department say they're actually very, very good signals, which we actually believe comes from this intimate skin character. And the real reason is why we look into this, the skin electrodes are wearable over quite some time. So we got the very same signals for half a day in our first prize. So this is ongoing research, and we will further look into this. But at the end of the day, we want to have more signals, and we want to use in a similar manner this graphene as a chemical sensor. So this, you probably know all this. You know that you can, via vicinity doping, change and modulate the conductivity of the graphene. This red bar should be moving. This is basically going from N-dope to P-dope material with ammonia. This has been shown in hundreds of publications, this type of works. But what you really need, if you want to make the sensors, you need a good selectivity. So you really need to functionalize this type of sensors. But if they work, they are good base because you have a quick analysis. It's quite easy to handle. You have a high sensitivity. It's scalable. Graphene gives you a good chemical stability and so forth. So those sensors or this material is predestined for a lot of sensors you can think of, but the main problem is that the inert graphitic or graphene material is not selective at all, except to P and N doping, and that you need to introduce something that gives you some sort of selectivity of various agents. So let's have a look at this type of functionalizations. So there are quite a few you can think of. You have different starting materials, single layer, few layer graphene, graphene oxide, or reduced graphene oxide. Also exfoliated graphene and so forth. And then you can think of a lot of different, let's say, chemical reactions, starting from covalent bonds, and pi stacking, going to pi stacking, or just adhering particles to it. But at the end of the day, you have to watch out that you always modify this material already during this step. So I pursued very much the idea of a non-covalent bonding of molecules, giving leaving the graphene in a pristine state and just giving that functionalities on top. So let's have a look how we do this, because the starting point is always this, that you grow your material by CVD on copper, and as shown before, similar to the electrodes, to the skin electrodes, you then have to transfer it with a wet transfer, usually with PMMA, onto some sort of a substrate. This has been investigated by a lot of groups. There's nothing special to it. I go to this. But what I wanted to show you, and this is an old images from a helium ion microscope we had in Dublin at the time, from various transfers. you end up actually with a material which is not that clean. And you can see that you have water bubbles underneath the graphene, you have ripples and rips, and then you have a lot of residues from your polymer transfers. This is here now cellulose nitrate, which show up in a helium ion microscope, but you wouldn't be able to see this in a normal SEM because the electrons wouldn't visualize it. So we started to look into this type of contaminations with a new method, because actually this machine is notoriously difficult to operate with TOF-SIMS, an instrument which we have. So TOF-SIMS is maybe familiar to those who worked in semiconductor industry. It's usually used for looking at doping profiles in semiconductor. So what it essentially does, it shoots primary ions onto the substrate and then sputters away the elements from the surface, which then go into an MS mass spectrometry analyzer. And this is shown here for a fingerprint of my student Rita. She looked at her fingerprint on a silicon wafer, and she can look at the sodium and the silicon peaks here. And if she just uses her fingerprint, you can nicely, if you map then the sodium and the silicon, you can see that the sodium just from touching the finger of the subject shows perfectly up in comparison to the silicon in between. So for all those who work in the clean rooms, that's why you should be wearing gloves when you handle your samples. But joke aside, you can tune this process, especially using different anodes that use super surface sensitive. And this is what we've been doing on 2D materials. But I said that I wanted to investigate the contaminations on 2D materials, but we use not graphene for this, but MOS2. Simple reason is the contaminations are usually carbon-based, and to investigate carbon on carbon is not so useful. So that shows better up in on MOS2, but in principally we believe that the very same things happened on graphene, as I will show you later on. So we use a standard process to grow this flakes of CVD MOS2, and again we get this T images. This nicely, we get some nice coverages of this crystalline material. And if we investigate this material when it comes out of the furnace, it looks really, really clean. We can look at the optical microscope as shown here. We can do AFMs, and we can see here in the cross section that we get a material which is about 1 nanometer high, which then is a bit puzzling because in theory it should be about 0.6 nanometer. And this is often shown for graphene as well, that it appears much thicker than in the cross section than it actually should be. Apart from this, it's a very nice and homogeneous and flat surface of the CVD material. Nevertheless, there's more of initial characterization. We can look at the Raman spectra without going into details, but we see the typical peaks for the Raman modes. We even see for the multi-layer region, the seed region. We can pick up the breathing modes and so forth. But we don't see any sort of contamination or anything like this on the pristine material. Same for the XPS. We pick up carbon, but you always pick up carbon. We pick also always up some oxygen. Nothing special to this material, except that it actually appears nice and clean. However, if you then go, which often has to be done through this transfer process, similar to what we do with graphene, that we take the MOS2 of the substrates with PMMA or polystyrene or PVA PMMA mixture. We can transfer it to any given substrate. And then we end up something like this. And if we then look into the material afterwards with Prof, we can start to identify on each of those samples the remainders of those polymers from the different transfer processes. Here you can then look at the mass spec of the molybdenum or the molybdenum carbos isotopes or the molybdenum sulfide species. And all the red peaks you see, this can be related to the polymers mixtures which had been used for transfer. In order to being able to quantify this, we used a bit more interesting methods or nice method. It's really, really hard to quantify the residuals of polymeric residues using the TOF-SIMS. But if you look at all the molybdenum peak, the molybdenum plus and hydrogen, we sort of can see that they only appear when the MOS2 had been in contact with a polymer, and we can then start to actually quantify those residues that come from basically the polymer on top of this by looking at the molybdenum species plus hydrogen, which start to form during the sputtering process before going into the mass spec. And this is a way that we sort of can visualize how much polymers we have in how much polymers we have left on the MOS2 in this study. And then we looked at the various annealing processes, for example, how effective they are for the different polymers. Annealing often being used for all TMD materials to clean them up. And we could show that some annealing procedures worked quite okay. For example, here for PMMA, 450 degrees anneal nitrogen worked quite nicely. However, not so much 150 degrees. And for polystyrene, 300 degrees anneal and forming gas, a mixture of hydrogen and nitrogen, worked okay, but we also could show that we never completely got rid in this of this polymers. So what you now think, what is new, everybody in the community more or less knows that you have some polymeric residues if they transfer the materials. We actually started to look with our TOF-SIMS a little bit closer into the counts. And this is now an example of the CVD clone material which has not been transferred. Something which I called earlier on nice and clean and very pristine. So this comes straight after growth at 700 degrees out of the furnace and into the machine, and this is the flakes we've been looking at. And in the TOF-SIMS we can nicely show the molybdenum. There's a bit more intensity in the double layer region. We see the sulfur, we see the silicon around the flakes, which comes from the substrate. We can see the oxygen of the silicon oxide nicely. But what we also can see is those peaks, and they show up preferentially on the flakes, as you can see. And those peaks can be associated with PDMS and a transfer polymer. And again, this material has not been transferred. It has not been in direct touch with PDMS, but it has been sitting maybe for a little while in a JPEG. And we can identify these polymers with this method by looking at the fingerprints of these polymers. And it even comes worse. This is a spectrum of the clean MOS2. This is a bulk crystal where we drilled in and cleaned it. So this is pure MO isotopes and no dirt. Again, this is not a monolayer flake. This is a crystal where we spotted away the surface and then looked at the spectrum. So this is really clean MOS2. This is a freshly exfoliated flake. So this is not CVD grown. This is exfoliated, but not in touch with the polymer. That's just from the standard mechanical exfoliation procedure. They use polymers in the vicinity to swart it, but not on the surface. And then you can see already this molybdenum plus hydrogen species showing up here, which then also can, and those peaks associated with PMMS. And to prove more or less our story, I can show you this. This is flakes that had been stored simply and for 1 month in a gel pack, the typical packs where you can store your samples in, and those PDMS peaks shoot up at the same time. This MO plus hydrogen peak should go up in the top SIMS spectra. So what this shows is if you have samples laying around in your storage area or on a gel pack, the PDMS will basically move or absorb onto the MOS2, and this can be even imaged here. This is a molybdenum peaks for the flakes, and this is a PDM peaks for this clean samples, the directly exfoliated samples and brought to the machine, and this is a PDMS peak on a flake which had been stored in a gel pack for about a month. Interesting to note is that the PDMS seems to preferentially absorb onto the MOS2 flakes. And to conclude the story, we just have been accepted at ASEAN as Nano after a long fight. There had been a paper from a Czech group in November last year, last November, 3 months ago, which basically see a similar thing, and by an STM study, AFM STM study, which also the composition and structure of ubiquitous hydrocarbon contamination on van der Waals materials. And they see this type of contamination where they see a bit of periodicity in there on HUPG, MOS2, HBN, and samples quite a bit, and they also come to the same conclusion that the contaminations have an extrinsic origin / they absorb onto the substrates. After a while, they actually leave the samples by on the ambient in the lab for a while to get these images. So this story seems to be consistent, and I think it's very interesting for everybody who works with those materials and with their surface properties. So back to the functionalization, what do we do? It brought us to the idea, because we assumed this as well, that we should start functionalizing at this stage the graphene before it gets contaminated with airborne polymers, also that we take it straight out of the furnace and functionalize it non-covalently with our parallenes directly on the copper foil directly after roast, and then go through the transfer process. And we actually had shown this already at an early stage, that we can get a nice and decent functionalization with parallene molecules on this directly on copper. And this is the process which we now have been used, this pre-functionalization here. This is parallene molecules to then do further functionalizing onto this parallene layer, which is then sits on top. So our integration scheme for graphene is, that would be the conventional way. We transfer graphene and stripe onto silicon and then functionalize it. We basically do the functionalization on copper first and then transfer the material onto silicon and then remove the layers, leaving it directly as a functionalized layer. And below you can see the difference of this functionalization route in direct comparison in the AFM and Raman maps shown here. This is the unfunctionalized material, which actually looks the dirtiest. The functionalized material is a conventional method. We get a decent surface at the end, but you can see quite a few remaining residues. And if you do this, what I call flat, this functional layer transfer, we actually get a very flat surface, which is fairly pure and on average a bit flatter than the other surfaces, slash meaning a bit more homogeneous. Here's a comparison of the height of the unfunctionalized layers and this functionalized layers with parylene. As shown here, we actually get more or less a monolayer, or what we believe is self-assembled monolayers of these molecules on top of the graphene. Those molecules carry then carboxylic functions, which we use further then for the attachment of antibodies, which is shown in the next slide. As shown here, we use this coupling reagents. This is the molecules we have. We have the carboxylic functions, and then we use this EDC NHS treatments to attach antibodies onto this functional layer on graphene. And what is shown here on the right side in the SEM images, that we actually can control nicely how much antibodies we attach to the surface. And this is done by that we attached gold particle markers to be basically to track how well our functionalization works. And we simply counted those in the SEM. And what I wanted to show you, if you used the wrong antibodies where the gold particles wouldn't attach, we actually didn't get any functionalization. And here we used different concentrations, and you can see that we sort of can tune the number, the density of our antibodies on our surface. And we made some statistics over this work. I have to admit that you get a lot of clusters also on the normal functionalized surfaces. However, they're much less homogeneous. So we actually believe that those things like to attach to, let's say, the polymeric residues quite a bit. So it's not so much about the absolute number, it's about the homogeneous distribution of those clusters, because they act then basically as binding site for the analyte, which is in this case methylamphetamine or colloquial language speed, a drug, which is very interesting because it's a small molecule, which always had been thought to be very hard to detect. But in the next slide, I show you that our meth antibody functionalized graphene sensors, we react quite nicely towards given analyte concentrations, which is shown here. You can see the shifts of the Dirac point or the changes of the resistivity of our sensors with the attachment and of or the exposure to the analyte. But let's go to the graphs where we averaged over roughly 60 transistors we made, and you can see a nice dependence on the meth concentration here And as a cross-check, we use paracetamol, where you didn't see any change in conductivity. And we have here the trend in the Dirac shift of the peak of the gated GFET. We used then as a check a different antibody which shouldn't react to meth, and indeed we didn't get the opposite reaction on this one. So that shows that our functionalization worked quite well and gave us nice results for a small molecule and with very little cross-contamination, and we just published this paper and go on to chemie. Okay, so this, I believe, shows that our functionalization route is quite successful. I'm not saying that other routes are not also successful, but we gain now very consistent results, and we can believe that we can functionalize now with also other antibodies. Just as a side note, we had shown that this parallel functionalization also works on MOS2. Here we used it as a passivation layer to then attach AL2O3. Here is a MOS2 FET, which is buried in with a parylene layer with aluminum oxide grown passivation layers on top shown like this. What I'm trying to say here that the chemistries on the MOS2 surface and the graphene surface with regards to these parylene molecules seem to work very, very consistent and similar. With this, I would like to switch gears and talk a little bit about polycrystalline TMD films and some sensors or detectors we made with those. As mentioned before, I'm not talking about this nice monolayer growth as shown before. I'm talking here about materials which we sputter or evaporate on top and then run sulfur or selenium over it and convert it to transition metal dichalcogenides. It's a relatively facile, easy to use method, and we've been working with this for quite a while, and we've been synthesizing quite a wide range of TMD materials with these methods. The usual suspects, MOS2, tungsten S2, MO, and selenides, but also we managed to make the tellurides of those two. But in particular, we had focused on platinum components, where actually platinum diselenide turned out to be a very nice material to make, and which I further on will talk about, but some others are possible. Here is some XPS structure which are available on all those materials and their stoichiometry according to XPS and Raman studies. The one thing we noticed looking at those materials is this procedure of converting a very thin metal layer, which is a perfectly scalable process because we essentially can do this on wafers quite nicely. You just need a good sputter or evaporation tool. That some of those materials, in particular platinum diselenide, can be synthesized at relatively low temperatures. And this is very important for silicon people because this is a so-called BEOL limit, which basically means silicon circuitry can survive below, some people say it's 400 or even 350, but roughly it's around this temperature. Also, aluminum leads can survive this temperature. So everything you can do below this temperature can be done on existing chips, let's say it like this. So that makes this a very critical process temperature if you want to integrate it with silicon circuitry. So that was the first thing that raised a lot of attention to this material. If you look at it, it's crystallinic in the nanometer range rather than the micrometer range. From the cross-sectional images, nicely aligns. Platinum diselenide in this case has a 1T structure. And we can make nice and layers, and as I said, that the low temperature allows us even to grow on glass or plastics, as shown here. So we can make nice and also big films of this, and we, as I said, we can make wafers of this, as shown here. And the second interesting point about this material that PTSE2 has a transition from being a semi-metal in bulk region. Here's a thickness going towards indirect band gaps semiconductor open up with below 3 layers. The band gaps open up, so we have a transition here, which always formed the idea that you have a transistor which could be contacted by thick semi-metallic platinum diselenide contacts going into a thin channel, which is then semiconducting, which is sort of shown here in studies, and could show this experimentally. However, with this method, we've never been able to make really switch the material off, because we didn't really get monolayer growth in the channel region. Nevertheless, we've been able to make such wafers, which went to the best transistors we had, were about on-off of several hundred, and mobilities of about 20 on this. But it also showed that they had a good stability in air. The mobilities up to 600 have been reported by other people. They also have high photosensitivity and piezoresistivity. And let's have a look at this applications. What I forgot, sorry. There also, those channels have been shown similar to what I've shown before. This is not now a graphitic channel, a PTSE2 channel, being extremely sensitive to NO2, and actually it's been shown that they are selective to NO2. Theoretically by those people, and our sensing results, gas sensing results with NO2 showed extremely fast response, extremely high response, and also a very good recovery. And this is, by the way, 10 devices measured at the same time in parallel. So that's basically the gaps between those two, and they also show the very same behavior, and we could have ppb range sensitivity for this gas. Photosensitivity, as I said, this platinum diselenide has a small band gap. It opens up, shown theoretically and also experimentally, it opens up for the bilayer and the monolayer. And we would have here in the bilayer something like 0.2 eV, while the monolayer should be ranging about 0.1, 1.2 eV. We used our polycrystalline films in this as a very simple photodetector by putting it on silicon. And in this structure, having the contact here and having here a contact region between silicon and platinum diselenide. And we actually could sense then some responsivity in the IR region as shown here. This would be the silicon region, non-IR, but the platinum diselenide gave us also some sensitivity in the IR region for photo detection. And this had been used now to integrate this on silicon waveguides as shown here, because this is very interesting, for example, for CO2 sensing, besides, of course, other photonic devices. So a lot of people been looking at creating photodetectors or modulators on silicon waveguide as shown here. Problem is, why graphene works quite nicely, it has to be mechanically transferred. There's no way of growing this material on top. You have to have the copper catalyst to grow nice graphene here. Not so the case for platinum diselenide or polycrystalline platinum diselenide. We can actually grow from platinum deposition on aluminum oxide and then conversion as to PTSE2 as I had been shown before. And this is exactly what we pursued, that we have a direct growth process, and here you can show, we could show that we have the silicon waveguide here and that we selectively could grow the PTSE2 on top of this region. Again, one of the advantages is that we have direct growth and no transfer, and that if you transfer on structured substrate, you always have the problem of reliability or ripping here at the sites. And this has been pursued in this Ulysses project. So we developed basically a conformal process based of ALD coating of platinum and then the conversion. And here you can see that we can, here's a cross-sectional image of platinum grown in the trench structures near the corner, that we have a conformal coating of these materials, and we actually managed to integrate this IR active PTSE2 channels on silicon waveguides directly. This is an image here. This is a schematic. That's a real image. You see the waveguide here, and the gray region is basically our PTSE2 photodetector on top of the channel. And here you can see that it actually we get some photo voltage out of it, and here's an on and off switching with the detector output. It's not the best material. Graphene had shown better results, but the beauty is that we can integrate it, and this was the first devices which we made, and we're pursuing this to let's say optimize growth on this for this type of application. And last but not least, I wanted to come back to the piezo resistivity of this platinum diselenide polycrystalline films. As I could show you, we could grow on polyimide directly. This is a SEM image of a PTSE2 film grown on polyimide. On the left-hand side, you can see this very same film with two silver contacts here, fully bendable plastic substrates. And we then actually could show that upon bending, it would change the resistivity of these films. And as shown here, this is a bending and this is a change in resistivity. So we more or less created a strain sensor in a very simple way by growing this material. We glued this type of plastic stripe onto a loudspeaker, and it worked up to even higher frequencies. You can see here 380 hertz, and it followed perfectly the film on the speaker membrane. So this is a really nice gadget. It maybe also has some applications in this body motion sensing, but it really raised the interest of people who do pressure sensors, and so far they've been using this graphene-based pressure sensors on cavities. The idea is that now the strain is changing the resistivity through the film. This is a standard technology for microphones and pressure sensors. In mobile phones, they use silicon membranes, but silicon becomes brittle below 300 nanometer are not stable enough. Graphene works nicely, however, is actually, it has a very poor gauge factor, and we believe with this PTSC2 membranes, which let's say are stable enough to span such a cavity as shown here in the very same manner as this immigrant. This is a substrate, and we have a PTSC2 membrane on top. This is a Raman tomography cross-section of this device. This type of devices has shown to give you a really big gauge factor. This is a resistant change in such a device. Here's a real image of the device over straining the membrane. Here giving relatively high gauge factors, and compared to all the other, let's say, nanomembranes which have been used from those materials, it showed really superior behavior. And if the device geometry and everything worked as well, we've got several magnitude higher response out of PTSC2 and this. And we're pursuing this PTSC2 type NEMS devices for pressure sensing and microphones in the flagship and also in national projects. So this was a lot of material for, I don't know how I am in time, probably too long time. But with this, I would like to conclude. So what is our takeaway images? Basically, the one is easy one, polymers everywhere. It's a real problem if you do work with sandwich devices or functionalization of this device. You really have to take some precautions. But I think I showed some ways how to deal with this, to be able to make this graphene-based biosensors. And in the second part of the talk, I showed that maybe this TAC process, where we simply convert metal layers, is a relative facile and scalable route to make polycrystalline TMDs, which do not perform in all regards, but for some of these devices, they're quite interesting. And in this case, I showed you these IR detectors on silicon waveguides and some perspective of this MEMS devices. This is polycrystalline membranes on top. And with this, yeah, I would like to thank my group and the collaborators listed here, and my former group at Trinity College Dublin as well, and then of course the funding agencies. Yes, and I think I would be happy to take some questions now. Thank you for your attention.
All right, thank you very much for that enlightening and interesting talk. Some quite interesting results in there. So we have a couple questions here in the question and answer box. So for technical reasons, I'll be reading them, and then we can see if there's a way to debate about it if needed. So the first question is from Christian Schaefer. He thanks you for the talk, and he has some questions about the contamination you found on the CVD growth of MOS2. And the question is about the explanation of the source of the contamination on the MOS2 that right from the furnace. Is it airborne hydrocarbons, or is maybe carbon being introduced during the growth process via backstreaming carbons? Do you use an oil pump or a dry pump?
Yeah. No, I mean, we've seen these contaminations on various substrates and also on mechanical exfoliated substrates. So we are very sure that this comes from airborne contaminations in the lab. In particular, when you use this, I mean, we usually take big precautions, but at the moment, even we have basically a storage cabinet with nitrogen to, you know, to keep it away from oxygen and so on. But somebody has somewhere a gel pack in there, or there used to be one, and that's enough. It's actually, the more I talk to people about it, a lot of people say, well, PDMS, that's very much known that this is airborne, and there's quite some works to get rid of it. I think people that ship even AFM tips in these boxes where they glue on the gel packs. You have some combination at the tip, at the start, and so forth. So it's actually relatively known, and the more this comes out, the more people say, well, we already knew this, but I think we are the first ones, besides this Czech group, that is actually able to visualize this really, and TOF-SIMS gives us even the ability to identify this. So we found on very clean and pristine samples always a bit of PDMS, which we believe comes from airborne hydrocarbons, in particular PDMS. If we did this transfer procedures or work with polymers close by, we got this type of polymers.
I see. And then Christian had a follow-up question, maybe related in the TOF-SIMS, correlating the MO plus H signal as an indicator for polymer residue. Is that a strong correlation, or could it be coming from something else as well?
No, this is maybe in the brevity of the talk, it didn't come across there. There's a good correlation between, the problem is if in TOF-SIMS it's really hard, you need to calibrate the samples to really, let's say, do it quantitatively and say you have so and so much polymer on top. But when you have different polymers, then the problem is that you can identify them, but you don't even know how easily they sputter away in this. So going from one polymer to another one, you cannot really tell how much is it, because you don't know how easily they ionize and what fragments you can get. There's a lot of art in this. But Rita had found that she can nicely correlate this MOE plus hydrogen species to, let's say, the level of contamination of it. And from then on, she used this more or less to have some sort of an indicator how strong the contamination is.
Okay.
Seems to correlate, but it's still, you know, on that level, it's all very yeah, indicative, let's say it like this.
Yeah, very complex problem too, I think. So we have another question from Antonio Pablo Perez. He asks, could you please explain a bit the temperature and precursor used for the growth of your CVD MOS2?
Oops. Yes and no. I don't know how. I mean, you probably mean the CVD grown flakes, this type of flakes. We used. I have to show you this image. We used a process which I maybe should. Can you see this still?
Yeah.
Which I should play the video here. We used a relatively special method, and what you can see here, I should stop the video here. We grew what we call in a microcavity setup. What we essentially did was to place two chips on top of each other. The upper one having the the molybdenum trioxide sputtered on top, and that would come from the very top of the substrate, while the sulfur simply was evaporated into the system. And this gave us, let's say, nice and decent growth of MOS2. Temperature, I think, was 800. I would have to dig out the paper. It's been described here in the scientific reports, 2014. For the first time, we called it the microcavity approach. The reason is, the main reason why we used is we had, let's say, a defined source of the molybdenum trioxide precursor. Most people just mix it somewhere in the tube. They sometimes get nice growth, but since you get this precursor everywhere in your tube, you then sort of get very varying results in the next runs. So this was a way to, let's say, define the molybdenum trioxide precursor. We just have about to publish very, let's say, full study using DOE's design of experiments for tungsten sulfide growth, where we actually were able to to tune this towards different properties, full layers, multi-layers, and closed layers versus flakes. So, but there's a lot of, depends a lot of also on geometry of your setup.
Okay. I'm trying to see if anyone has any more questions. Feel free to post. I'll ask one quick question. For this TAC process for growing platinum diselenide, how much degree of control do you have over the layer thickness there?
Very, very good question. I even have Sarglac, and you probably know this from the project. It's
yeah, it's a general curiosity.
Yeah, I just chose, since I have the slide, I should have we even published this. I mean, this is what I'm trying to tell people. We have good control down to a nanometer. Let's say it like this. So for multi-layers, we get decent growth, but if we always, when we try to go down to the monolayer, we tend to get discontinuous films. So basically, you sort of have an island growth, and which is known from platinum. And rather than getting nice monolayer film, we get sort of a patchy film, and then being not conductive at all. And if you look at some of the TEMs we get, I don't know if they show up. I maybe go to just really quick on the presentation mode. We sometimes get cross-sectional images like this, where we have here a 5 nanometer film, which seems to be perfectly aligned here. And then we have the next sample in regions where it looks very like this. And this is good and bad at the same time. That means we sometimes get this monolayer properties in the films with very thin patches, but we also have, let's say, patches of other parts. This is to the level where we get, and so far efforts growing those films as a monolayer, we used MBE type of platinum and so on. It all didn't work. But recently there have been a few reports on MBE type of growth, which seem to get close to monolayer film growth, let's say it like this.
Okay.
Can be better than what we do currently, what I should currently.
We have one more question now from Christian Schaefer. For your microcavity MOS2 growth, how big are the substrates you use, and how good is it for large area homogeneity of these TMDs?
The samples we use are a centimeter square in this case, in a tube furnace. I would believe that this process is not good for full wafer scale. Because very much we already see over the sample region that there are differences because of the microcavity. For the larger substrates, we actually go to hydrogen sulfide precursor and metal organic MO precursor, which is typically done in wafer scale furnaces. But you talk about an investment of at least $500,000. Because you have very toxic precursors and big tools. I don't know if you have the capabilities at ICM2, but the problem again is the nice crystalline monolayers are still very hard to grow with this process. But if he wants to learn more about this microcavity approach, I'm happy to answer details or connect to my students here, which currently pursue it.
Okay, that's great. And then I think, oh, here's another one. Yeah, he says, yes, we use MOCVD. So, okay.
Yeah.
All right, yeah. And then I'll ask one question for Hugo Gómez, our first speaker. So Hugo, you demonstrated this more precise approach for measuring heat capacity in nanomaterials. So I was curious, are there particular systems or materials you're interested in applying this approach to in the future?
Right now, we are only focusing on the small diselenide monolayer, which is the main goal. But yeah, in the future, we would like to try with another 2D material, and also with structures, stacking different monolayers of different materials one on top of each other, to see what how this capacity in the monolayer will be. But yeah, for the moment we are only focusing on this molybdenum selenide monolayer. Yeah.
Okay, thank you. All right, looks like we've covered all the questions in the chat and everywhere else. So with that, I'll thank you, Hugo and Professor Duesberg, for your talks and taking the time to chat with us today. And if there's nothing else, then I think we can close the seminar here. So thank you all for your time.
Thank you.